In this section, we're going to talk about the first derivative test. And to start out, we're going to talk about when functions are increasing and decreasing, and how this is related to the first derivative. And this is kind of already obvious because we know if the derivative is positive, the function is increasing, and if the derivative is negative, then it's decreasing. Okay? But this chapter starts out with a corollary to the mean value theorem. So they call this corollary 3. And I'm going to show this proof because it's fairly simple. And it gives you another example of how the mean value theorem is used. And kind of what's important about this theorem is it tells you what the function is doing over an open interval. Okay, so it's telling you that it's going to be either increasing over an interval or decreasing over an interval. And so suppose f of x is continuous on AB and differentiable on AB. So on the closed interval AB, differentiable on the open interval AB. So that's those important conditions for the mean value theorem. And so now it says if the derivative is positive for all the values of x in the open interval, then f of x is increasing over the whole interval. And then if the derivative is negative for all the values x in the interval, then f of x is decreasing on the interval. So let me show you then how this would be proved using the mean value theorem. So we're going to let x1 and x2 be any two values in the interval. So we're just randomly taking any two values in the interval. And so what I'm going to want to do is either show that it's increasing or decreasing. So to show that it's increasing, then let me say here, let's assume x1 is less than x2. So assuming that, and it could be either way, but assuming this, whichever one's smaller and one's going to be bigger, then the way that I would show that the function is increasing is if f of x2 was bigger than f of x1. Okay? And it would be decreasing if f of x2 was actually less than f of x1. So how are we going to show this? Okay? Well, notice this here, that f of x is continuous on this closed interval, x of 1, x of 2, and differentiable on x of 1, x of 2. Okay, because, well, I guess we're given that these two are coming from this interval here where it's differentiable or continuous on the closed interval, differentiable on AB. x1 and x2 are in the interval, but if it's it'll be differentiable there according to this condition. And if it's differentiable, it's continuous at those endpoints. So if it's differentiable at x1, x2, it's going to be continuous there. So we got this. Also, we're told that the derivative is greater than 0 for all x in AB, and so that means it's going to be differentiable at those x, at any x value. Okay, so we would have it there too. So basically, you wouldn't need this first condition because you're kind of given it right here. Okay, so so we're going to apply the mean value theorem to this interval, x of 1, comma, x of 2. Thus, there exists a C in x of 1, x of 2, such that, and I should say in the open interval, sorry, such that you get that f of x1, or f of x2 minus f of x1 over x2 minus x1 is equal to this derivative. Okay? So now what I'm going to do is I'm going to move this up to the other side. Okay. So notice this is going to be positive, right? Because we're assuming that x1 is less than x2. So, and I'll put these two cases over here, okay? So this is, we'll call this case 1. This is where the derivative, or we'll say, so one of these two cases would be the case. So when the derivative is greater than 0 over the interval, then this is positive. And then what that means is the product is positive, and so this will be greater than 0. So f of x of 2 minus f x of 1 is greater than 0, and you're going to get f x of 2 is greater than fx of 1, and that's what you needed to show. So this is pretty straightforward. So when the derivative, this is the first case, when the derivative is greater than 0, then you get that the function is going to be increasing, because these are any two x values in the interval. Okay, well, case 2, you can probably already see f prime of x is less than 0. Okay, so that would be this case. Well, in that case, this is positive, and then this would be negative. And a positive times a negative is negative, so that means this here, f of x of 2 minus fx of 1, is going to be less than 0. And so you get fx of 2 is less than fx of 1. And that's what we needed to show that it's decreasing. So this is increasing, just like it says here. And this is decreasing. And you can show this for any points in the interval here, and so that means it would be increasing over the entire interval, and this means it would be decreasing over the entire interval. And so this gives you another nice example of how that mean value theorem is used here to prove something. It sets this up so that you can actually start saying meaningful things about the relationship, which one's greater or less than or whatever. Okay, so that mean value theorem, this is kind of the idea of how it gets used in lots of different theorems. Okay, it's an important theorem. Okay, so now what we're going to want to do then is, given a function, we want to know what intervals is that function going to be increasing and what intervals will the function be decreasing. Okay, well that depends on the derivative, right? If the derivative is positive, whatever intervals the derivative is positive, the function is increasing. And then whatever intervals the derivative is negative, it's decreasing. Okay, and if we're dealing with a nice continuous function, then what it means is the places where it could go from positive to negative would be at the critical points of the function, because it would have to pass through 0. The derivative would have to pass through 0. It would have to cross the axis to go from positive to negative. And so to determine these intervals, what we're going to do is first find the critical points of the function. So if you remember, the critical points of a function are either where the derivative is equal to 0 or the derivative is undefined. So this is a cubic equation. Okay. And so taking the derivative, bringing the 3 down, subtracting 1 from the exponent, minus 12. So that would be the derivative. And so now set this equal to 0. Okay, and then we need to solve this in order to find the critical points. So I factor out the 3. Sorry, this would be 4. And then I can factor this apart, right? Into x plus 2, x minus 2. Okay? And so either x plus 2 has to equal 0 or x minus 2 has to equal 0. So either x is equal to a negative 2 or x is equal to 2. Okay? So we have a cubic, we got this quadratic, we're finding the zeros of a quadratic equation. So it's when you're finding critical points, you're taking the derivative, setting it equal to 0, and solving the equation. Usually you solve it by bringing everything to one side, which it's already on one side, because you're setting it equal to 0, and then factoring, and then setting the factors equal to 0. Okay? And we find these two critical points. And of course it's defined, the derivative is defined, it's a parabola, it's defined everywhere. And so there is no critical point when a critical point is either where the derivative is equal to 0 or the derivative does not exist. It's not defined. Well, it's defined at every point, and so these are the only critical points of the function. That's what I'm trying to say. And so what you can do is you can kind of set up, set up 3 intervals here. And these are like the critical points. This is negative 2. This is 2. And so you kind of got this interval over here, negative infinity to negative 2. And then you got negative 2 to 2. And then you got 2 to infinity. And if you notice, the theorem we just did are dealing with open intervals. This is proven for open intervals. And what that means is even if the open interval involves an infinity, this still works because I could still pick 2 values out of here and do the same thing of what I just did. The theorem will work even with infinity. So this breaks up the domain of the original function, okay, and now I know the derivative is 0 at these points. It's continuous over the range. So all I need to do is test at one point over here to see if the derivative is positive or negative. Okay, so what I can do is just pick one value. So maybe I'll just pick negative 3. Okay, if I pick negative 3, then f prime of negative 3 is going to be 9, 27 minus 12. And that's going to be 15, positive 15. And so I get this. I get f prime of negative 3. Or f prime of x here, sorry, f prime of x. So all you got to do is test one point in this interval. If it's positive, then I know over this whole interval the function is positive. Okay? And you get this from the intermediate value theorem, because there are no zeros here, and in order for this thing to change sign, it would have to go through 0. Okay, so the derivative is positive here. So let's pick a test point here. I would just pick 0. That's easiest. Then f prime of 0 is negative 12, and so I get f prime of x less than 0. It's pick one value, and you can pick the easiest value like I did in this case. If it's negative at that value, it's negative over the whole interval. Okay, and then here maybe I'll test 3 again. I'll test not negative 3 but 3, and then f prime of 3 is going to be 15 again, and so f prime of x is greater than 0. Okay, And so this is where the function is increasing. Over this interval it increases. This is where the function decreases. And this is where the function increases. And so what you can do here, when you can pause the video, or when you stop this video, you can go ahead and graph it and check and see if whether or not this is the case. So go ahead, you can stop the video and graph it, and then in the next video we'll use this. We'll start with this example, and then we'll explain the idea behind the first derivative test.